Circuit theory looks difficult only until you realize you've been using its logic since childhood. Welcome to the Learning Studio, where we don't just teach subjects. We break them down to their core intuition so you understand why things work, not just how to solve questions. Most people think circuit theory and analysis, covering resistive circuits, RLC circuits, and nodal or mesh analysis, is a complex, math-heavy topic that only makes sense after formal electrical training. But in reality, this subject was never created for exams. It was created to solve real problems involving energy flow. Long before it became an academic discipline, the same logic was already being applied intuitively in everyday life. Think about how electricity behaves inside your own home. When too many appliances are connected to a single extension board, it overheats. When devices are distributed across different sockets, the load balances naturally. When you switch on a fan, it doesn't reach full speed instantly. It ramps up over time. Without realizing it, these everyday experiences already follow circuit theory, where energy flows through multiple paths, faces resistance in some components, and is temporarily stored in others. At its core, circuit theory explains how current chooses paths, how voltage distributes itself across interconnected points, and how energy responds over time depending on resistance, capacitance, and inductance. This intuitive behavior is exactly what nodal and mesh analysis formalize, allowing engineers to calculate what is happening at every junction and loop inside a circuit instead of relying on trial and error. On a much larger scale, the same principles govern how electricity is delivered across entire cities. Power distribution networks rely on circuit analysis to maintain stable voltage, prevent overloads, and ensure safety, while at the device level, everything from smartphones and laptops to electric vehicles depends on precise circuit behavior to function efficiently and reliably. In practical engineering work, circuit theory is applied when designing printed circuit boards, diagnosing faults in electronic systems, optimizing power consumption, and ensuring components operate within safe limits. These ideas were later systematically formalized through the work of thinkers like Georg Ohm and Gustav Kirchhoff, who recognized that electrical behavior follows consistent laws that can be modeled, predicted, and scaled, which is why circuit theory remains the foundation of all modern electrical systems. Now that this intuition is clear, the next step is to move beyond steady behavior and understand AC circuits and phasor analysis, where time-varying signals introduce a new layer of complexity. And that's exactly what we'll explore in the next video here at the Learning Studio.